Hi. Today we're going to get to do a little bit of drawing, a little bit of geometry, a little bit of things that we haven't seen too much of in chemistry yet. I mean, yes, we've seen some drawing, but on that note, I'm going to quickly draw the structure for water, something we've seen in class a few times already. There could be a bit of a question that you can have in your mind that says, you know, I understand that when we draw our atomic Lewis structure for oxygen, that it ends up with two pairs, two unpaired, and if you follow my way of drawing it, the oxygen hydrogen or the hydrogen oxygen hydrogen angle ends up always being this 90-degree angle, as I showed. But I also said that, when it comes to Lewis structures, it doesn't matter where you put the electrons because Lewis structures are not a representation of actual geometry of molecules. And that's a big shortcoming of a Lewis structure. They tell you how all the bonding happens, but they don't tell you where everything is actually located. So technically, both of these structures convey the shape, or not the shape, convey the bonding in water. Two shared pairs, two lone pairs. That said, if we knew stuff about how water behaves and how it looks, could we pick one of these as a better structure moving forward to identify what water looks like, so that even though we don't draw it in 3 dimensions, we can at least represent it on paper and have a discussion without getting confused? And the answer is yes. Enter valence shell electron pair repulsion theory, which states that if you have more than one pair of electrons on a particle, you can imagine that these electron pairs have the ability to float around the surface. Like, imagine you have like a tennis ball. The electrons have to be somewhere on that edge. And the idea is also, that electron pair can be a lone pair or it can be a bonded pair, where you can imagine, like, basically you've got a bonded atom and it can like rotate around in a circle and it can move around to different positions. On top of that, if there's more than one pair of electrons on that central atom, you have to consider that there is a bit of a repulsion between pairs of electrons. Yes, electrons pair up, but the pairs themselves have a repulsion for each other because they're negatively charged. Where if you've got one atom bonded here and another atom bonded here, there's going to be repulsion and they will repel each other. Now, they're not going to swing all the way back around. They will level back out to some place where their distance is maximized while still being located on that same central atom. And you might be able to picture in your mind what 2 would look like, but then what does it look like when you've got 3 and 4? And by drawing what these 3-dimensional structures might look like, you can start to say, yes, that's what shape this molecule takes. And what it comes down to is how many electron regions, like I said, 2 or 3 or 4, otherwise known as electron domains. So you can see here I've listed all the things that constitute an electron domain. And I think the best way to show what an electron domain is through several examples. So let me draw these structures. I'm going to start by drawing the atoms. If you want to draw these structures yourself for good practice, feel free to pause the video. So, of course, in each case, the water that's there is the same as the water we had before. So now we're just going to make a bunch of single bonds and then double bonds where needed. This is a single, this is also a single, and this one can wrap around and be that single. Here, again, we want to make single bonds to as many atoms as possible, and then I think this one has to come down here and make a double bond. So now I'm going to clean all of these up really quick. And there you go. For each of these molecules, we should now go through and determine the number of electron domains, because this will help determine what shape these molecules take in 3-dimensional space, assuming that the electron domains are free, rotating, and allowed to separate distance-wise, angular-wise, as much as possible. And so again, we're maximizing that angular distance. In this case, let's count up. We see a single bond, a double bond, and a triple bond all count as one domain. So that's 1, 2. We have 2 electron domains. Here we've got 1, 2, 3, 4. Lone pairs and single bonds each count as a different domain. That's 4. For COCl2, we've got 1, 2, 3. No lone pairs. A double bond counts as 1. That's a total of 3 electron domains. And for water, just in similar to NF3, we've got 4. The difference is 2 lone pairs, 2 bonds versus 3 bonds, 1 lone pair. So that's going to be our starting point. We've got examples of 2, 3, and 4, but I figured here would be a good idea to talk about 2. As I showed on the previous page, when you have your central atom, I'm going to represent here as X because there is no element X. You can almost imagine putting these bonded atoms as like almost like toothpicks, like sticks, like you stick it in. Now, if you try and add a second pair of electrons, depending on where you put it, like I said, there's going to be some repulsion. Here, they're going to repel each other, and they do repel each other. They both move. And when they both move, if they swing too far, they're going to bounce back. And there's going to be like this wobble until they level out. Maximum repulsion for 2 electron domains would be 180 degrees apart. You might be able to picture that one in your head. The molecule that you make looks something like this, and we call this shape linear, as of course you might have guessed. And so the idea is, like for CO2, for example, we treat double bonds and single bonds as the same because it's 2 or 4 electrons shared between 2 atoms, but they're still locked in being shared between those 2 atoms. So this would be like here if, where's my pen? Oh, there. This was the C, and this was the O, and this was the O. For 3 electron domains, we had our example of COCl2. And similar to the example of linear, right? If we just added a third one in there, we would see a repulsion. This one would be pushed down, and this one would be pushed to the left, and this one would be pushed down, and this one would be pushed to the right. So you kind of see how this one would be canceled out, but then the other 2 would drop down. And they would only drop down so that the distance between the top and the side is the same as the distance between the 2 sides. And I think what we would get is a structure that looks something like this, where the angle between all 3 of them is going to be 120 degrees, right? 360 divided by 3. It's like the inside somehow of like an equilateral triangle. This also does happen with BH3. I'm going to draw really quickly just the atoms. Like carbon, there's a bonding carbon and a non-bonding carbon. And so the non-bonding boron definitely has 2 paired electrons, 1 extra, but we do want to spread these out because, in the case of carbon as well, we want to make as many bonds as possible. And what we get is a structure that looks like this. Now, this is kind of interesting. Boron is a great example of 3 electron domain geometry because boron as an atom only has 3 valence electrons, which means it can only make 3 bonds for a total of 6 electrons around that boron. That's not a stable octet. Interesting. To get a stable octet, maybe you could dump in some extra electrons, but then it would have a negative charge, which that isn't too stable in and of itself. So there's this wonderful balance for boron between having a neutral charge but being electron poor versus being electron well off in electrons, but then having that negative charge, which is a little bit less good as well. But in both cases, COCl2 and BH3, both of these are the same geometry because it's still 3 electron domains. And to draw that one out, you get a picture up here, and the name is trigonal planar. Planar as in like in 2 out of 3 dimensions, right? They're still like flat molecules. And this gets a little bit more interesting as we talk about 4 electron domains. So really quickly, we've got methane, and we've got ammonia, and I think we've seen all of these before. There's water again, and hydrogen chloride. I'm just shortcutting straight to the structures. In each of these cases, we go from having 4 bonds, no lone pairs, to 1 bond, 3 lone pairs, but it's still a total of 4 electron domains. And so trying to draw this out, you might think that we want to do something like this. You have your trigonal planar arrangement, and we add 1 more electron domain like before. It doesn't matter which one you pick, you put it there, right? And then there's going to be a repulsion this way, and then there's going to be, repulsions there on that middle one, and those 2 will pop up, but they won't pop up too far because then there's still another electron domain above them. And what we get is this structure that you think might look like this, where all the angles are 90. That's all equidistant, right? Except it isn't, because we're not thinking in 3 dimensions. You know, if we had our flat planar molecule, I want you to try and imagine taking that molecule and rotating it like this. And you can see that between the top and the bottom, the angle is actually 180 degrees. And VSEPR theory does work in 3 dimensions. You want everything as far apart as possible. Equidistant from each other is best. So how do you get 4 electron domains all equidistant from each other? Well, I think the thing is you have to think about it in 3 dimensions. So I want to try and take this trigonal planar structure that doesn't have this new electron domain in it, and I want to try and rotate it. I want you to try and picture in your head taking and rotating. I'm going to try and draw it, and it would look something like this. Now, the way I'm drawing this, I'm trying to say that this A with the fat filled-in triangle is coming towards you, and the A with the dashed line is swinging back away from you, kind of into the screen and out of the screen. So we're still working in 3 dimensions. I took your 2-dimensional thing that you drew and I just rotated it 90 degrees. Now I think we have a chance to add a new electron domain right there. If we added a new electron domain on this face where there's nothing right now, it's completely devoid of any electrons, we put it there, there's going to be a repulsion on all 3 of these, which is kind of neat. That works really perfectly because they'll repel each other until they start repelling, within themselves, and they push back a little bit, and then they'll establish that nice place where all of the electron domains are equidistant. And what that ends up looking like is it's not this 90 and 180, and it's not the 120. It looks something like this. I'm trying to let the shape of the A or the size of the A dictate how close it is to you. But again, one of the A's is coming towards you, one of the A's going away, and then in the plane of the drawing, you've got the one going up and the one coming down to the side. Here, you get all angles to be 109.5 degrees. Even this one, which doesn't, might not look at it. This looks a lot smaller, but it's still 109.5 degrees separated. And to draw it out in 3 dimensions, it looks like the structure in the upper left, and this is called tetrahedral. And to show you what that looks like, I have this. I found this dog toy in my backyard, actually, when I moved into this house. So I took it and I cleaned it up, and I figured I'd use it because this is a toy that has 4 different spheres all kind of mushed together into one shape. And it's done so to make sure that all the spheres are equidistant from each other. So this is your tetrahedron. If each of these, if you were to connect them with a flat piece of paper, the surface that you'd make would be a tetrahedron. This is not, because it's got these bulbs to it. But I like these bulbs because you can kind of picture each of these as a bonded atom, and in the center would be that central atom. So if this was methane, each of these would represent a hydrogen atom, and the carbon is jammed into the middle. So this is where you get your 109.5, and if it's making any sense, you can kind of think of it this way, right? So you can think of it this way, where there's 3 in the back and 1 in the front. Or if I can hold it right, I think I want to hold it this way for the camera. Yeah, where this one and this one, these are the ones that are in this plane. This one's obviously coming towards you, and then there's one back here that's coming away. It's kind of hard to see this way because I'm trying to align it a certain way, but this is what your tetrahedron looks like. So now that's all well and good, right? The angles still get closer together. We got 109.5 instead of, the other, something a little bit less helpful. But this doesn't really get us any closer to talking about water, I don't think. Right? Because water, maybe it does. Water is tetrahedral in nature, but there's a big difference between water and methane, in that methane has 4 bonded atoms and water only has 2. And so what we have to talk about is, how do we represent this on paper? I'm going to put these 2 lone pairs here. We can kind of imagine that's what that looks like, right, with those 2 there. But, does it matter? Can I instead draw water like this, and would I come out with something a little bit different? I mean, is there a reason why we should be drawing either that right angle water when we draw a Lewis structure versus that linear water? And I think looking at these, it really makes it really like makes more sense to me to show. There's a difference between what we call electron geometry and molecular geometry. And electron geometry is all electrons on a central atom, and molecular geometry is just bonded atoms. Now, the shape that the bonded atoms make is influenced by the lone pairs. So it's not to say that the lone pairs don't count for electron geometry. They count. They shape where the atoms go. To try and make a little bit better sense of this, I want to look specifically at water. So I'm going to write electron and molecular, right? Electron and molecular. In the case of methane, the electron geometry is just based on your electron domains. That's what we did before. So this is tetrahedral. Since there are no lone pairs, we also say that the molecule itself is tetrahedral. And so if I could grab a highlighter really quick, actually. Let me change to a color I can actually, yeah. So that we count all 4 of these bonded angles, and then so the shape that we make, if we connect all of them, is like this triangle pyramid where you've got these triangle faces, and there's 4 of them, and that's the whole molecule. In the case of water, though, the electron geometry is the same. We still have a tetrahedral electron geometry. But if we looked at just the molecular geometry, there we go, we're only going to count the oxygens and the hydrogens. And you can kind of see in both of these structures, as I've drawn on the paper, it's not in a straight line. It's got an angle that's not 180 degrees. It's something else. And I'll show you what this is with this 3D structure in a second, but I do want to make sure I at least get the name on the page. This molecular geometry is something called bent. And I think you can see what I mean when you just look at the pictures, but I also have this. To look at this, it might not be so easy to see until I label it, but if this was water, 2 of these would be lone pairs and 2 of these would be hydrogens. So I'm going to label this one as a hydrogen. And then, you think like, well, which of the other ones do I label as a hydrogen? And what's kind of nice is it doesn't matter, because if you consider this one electron domain as a hydrogen atom, all the 3 others are all adjacent to the hydrogen. That's the nice thing about it being equidistant. So if we put these 2 here, it doesn't really matter if they're here or they're these 2 or they're these, whichever 2, they're always going to be right next door to each other. And so this is going to be your molecule here. These 2 lobes impact the shape that the hydrogens take, but it's just a cloud, right? There's no nucleus there to really like kind of see as well. So when you think about the actual molecule itself, it's going to be this shape like this, where it's bent. And the angle is about 105 to 110 degrees. But just to make sure we're on the checkpoint here, for each of these structures, I want you to come back and figure out the molecular and electron geometry for each. We drew COCl2 already, and OF2. And so just as before, the electron geometry, we're just going to count up the bonding domains. Here we've got 3, just like we saw before, and so that would be trigonal planar. Here we have 4, and so that's going to be tetrahedral. The molecular geometry here is going to be based on the bonded atoms, and you can see we still have 3 bonded atoms, no lone pairs, so they're going to match. But for the OF2, we're only going to look at the bonded atoms. And here we've shown when you have 2 and 2, this is a bent configuration for that OF2. So to sum things up, should we be drawing water in a linear or right angle fashion? Well, based on what we've got here, and especially when you're looking at OF2, which seems to have a lot of similarities to H2O, since it's based off of that tetrahedral geometry, it would be doing us a disservice. I mean, you could you could hold your molecule, your structure. Hypothetically, you could hold it like this and make it look like it's in a straight line, but that's not really best representing what this really looks like. So I'm not saying you have to draw these angles and these wedges and these dashes. You don't have to do that. But when it comes to drawing water, you're really not doing the right thing if you draw it linear. I think you should be drawing it bent. Thanks for watching.